one more thing in this list of 4 sets of summary measures. Maybe a little bit premature given the way the structure of the course, but still, let's take it here. Namely, the concept of looking at 2 different variables at the same time. We will get back to that later in the course in a more statistical way. For now, it's the descriptive statistic approach. So here's a plot of heights and weights. And I have made a so-called scatter plot. I see mean height here was 178 centimeters, mean weight 78 kilograms. What's the story about height and weight here? Is there a relation between height and weight, between weight and height? Yes, there is, right? I mean, we have a pretty clear positive pattern like this, right? Here is almost an ellipse, personal ellipse, expressing that it seems in these data, which will come as no big surprise if we have a little bit of understanding of physics, that people that are higher on average seem to have more kilograms, since there are some physical rules when it comes to volume and height and so. So people that are higher are on average also heavier. How could we quantify that? That's the thing. Could that be quantified by some kind of number, this relation, or what it is also called the covariability? Now I talked about variability, the variance of a single. I could compute the variance of the heights. We tried that already. I could also compute the variance of the weights. We discussed that a little bit. We didn't try it. Then I could combine the 2 concepts and define something which is called the covariance. And to emphasize that we are primarily today talking about the sample covariance, the one that we can have 2 columns of data in our data set, and then I can compute this number in which I take it, it's the same parts that go into the variance, but instead of squaring the deviations for either x or y, I take and combine the x deviation with the y deviation and multiply them together. And then I add up all those 10 terms where I have combined. If I do like that, look at what happens. Actually, I think I would. Sure, and then we go back. I have one more thing to mention from that slide. But let's just emphasize with a bit of small numbers. But here are the numbers. Then I look at, for instance, student 1 here. Student 1 was 10 centimeters below average height, and student 1 was 12.6 kilograms below average weight, right? Student 2, this was student 1 here I was looking at, right? He is below both on the x and the y. He's in this quarter down here. And so is 2 and 6 and 3. Whereas 10 and 4 and 5 and 8 and 9 and 7, they are all above average, both on the height and on the weight, right? So when I use my new covariability measure like this, when both of the numbers are negative, the contribution to the covariance will be positive. When both of them are positive, the contribution will also be positive. So in this particular example, where I do not have anything up here or down here, they are all positive. So I hope this is, I'm not proving anything, I'm trying to showing that this definition of covariability makes sense in the way that when I have a positive pattern, it will give me a positive number, such that when you understand that, we can use that when we see a positive covariance. I know, yes, that tells me that the relation is a positive thing like that. So it's to understand that the measure is doing what it's supposed to do for us. And I hope you could follow me just a little bit there. All these are averaged, again, by n minus 1. Then it has a complicated unit actually, because it comes with x units and y units. So it's actually centimeters times kilograms, such if you're a physicist, right? Physicist, I think is the right word, right? I always mix it up with the other one. There is a standardized measure, a similar measure, that is called a correlation coefficient. It is, in a way, almost the same thing, if I understood in the right way, in the sense that if you compare the definition of the variance up here, of the covariance, I should say. This is the covariance. It is basically the covariance divided by the two standard deviations. So you sort of standardize this measure of covariability to sort of a standard scale by dividing by the actual standard deviation of x and the actual standard deviation of y. It could also be expressed explicitly like this, in which, if you want to be formal about it, it's the covariance between the standardized numbers. The numbers where you have taken the original numbers and divided by the standard deviation. And then you take the covariance of these two, that is the correlation. But it doesn't matter whether you divide by the standard deviations here or here, it's the same thing. Let's look at the example. The covariance was 166. A covariance as a number is difficult to interpret. What does it mean, 166? Now, I can take the standard deviation of heights, of heights, 12 centimeters, standard deviation of weights, 14 kilograms, and I divide by those, and I get a correlation of 0.97. This is a number, the correlation, which we know something about. It will always be between -1 and 1, by definition. It is exactly -1 or 1 if the numbers lie exactly on the line. Rarely so for real-life data analysis. That's a mathematical thought that that's what happens. It measures on this standardized scale the degree of linear relation between x and y. Positive if it's going positive direction, negative if it's going negative direction. It all makes sense. For instance, I have something with the sign there. This is 0.95. This is minus 0.5. This is approximately 0. And then an interesting point, this is approximately 0. This is just to warn us a little bit about getting too enthusiastic about this number. It's a linear measure. It's a measure of the strength of linear relationship. So 0 could mean this. If I put in a line here, we're going to put in lines in these patterns in a few weeks. It looks like this. If I put in a line here, it looks like this. Would the line be a good story about what's going on here? No, not at all. What about here? No, not at all, but for a different reason somehow. Here, at least, it doesn't change anything whether I put in a line, because it doesn't do anything to me, the line. Here, the line would be a pretty strong mistake to make if I want to use the flat line for anything, because the truth goes like that. So the line is by no means a good way to deal with the thing. The line over here is actually as good as you can do anyway, because the variability is just large as it is. But there's a big distinction between those two situations, of course. This also tells us that linear patterns like this, correlation coefficients, should always be validated by double checking that you don't have obvious non-linearity things going on in your situation, because then the correlation coefficients basically is not good for any much good English there. Now it's your turn. Can you guess the correlation? You red guys, you should go back and check the chapter on correlation, or we are just having fun. Negative, that's when it's going down, right? Positive, that's when it's going up. I think we had a complete change of, didn't we? Good to see. Now this is a very, very poorly, it's designed like computer games from the 80s or something, but nevertheless you can guess the correlation. And I'm challenging you. No matter what average error you get, I'll beat you. I'll beat you in the open. No one can beat me on this. If you dare, you can practice. We can do an open game on the last day and I'll beat you. You can be as good a computer gamer as you don't. This is like standard computer games from when I started with computer games in the 80s. So you won't win anything on being good at all. I don't even know the name of these guys who won the world championship. What's that called? Warcraft? Was that? No, what's the thing? Anyway, as you can hear, that's how much I do computer games myself, apart from guessing the correlation, because I'm the best in the world of guessing the correlation. So if you can win $1 million on guessing the correlation, I would be the winner. Anyway, let's see about that if you can beat me.